questions? There are no questions. We will have time anyway in the networking session afterwards. Thank you very much for taking your time. And now we give the floor to Maria Giovanna DAINOTTI. She has the unique position of being associate researcher at the National Institute, Astronomical Institute of Japan, and coming from INAF, from Italy. So she speaks both as an Italian and a Japanese, being an expert of gamma ray observation in space. She will talk about this. Thank you.
Thank you so much for inviting me today, and I will tell you a little bit about gamma ray bursts and how these are important for astronomy. I'm a permanent assistant professor at the National Astronomical Observatory of Japan, and also concurrently serve as assistant professor at Sokendai, which is the associated university with many laboratories. And what are the key open questions that we would like to solve? So we have observation in different electromagnetic bands, and we would like to have an advantage to use them all, as it was said by the first speaker of this session, for solving some of the most challenging problems in particle physics and astrophysics. We have already heard that one of the main questions is that can we prove that galactic cosmic ray acceleration mechanism is provided by the supernova shock waves? Are the galactic objects able to accelerate cosmic ray up to the 10 to the power of 18 to 10 to the power 19 electron volt? And one of the questions that it is closer then to my field is that are the galactic nuclei, the gamma ray bursts, also some other still unknown mechanism, the source of cosmic rays at this 10 to the power 20 electron volt? But of course, before going into the details of this question, one needs to understand also what are the mechanisms that trigger gamma ray burst. And to answer the questions, we really need to have a joint effort between collaborators, between scientists, and therefore this is what we did in 2022. I joined the NAOJ in January 2021. Then we had the Mr. Ambassador coming to visit NAOJ in 2021, and we started the discussion on how we can make this collaboration between INAF and the NAOJ happening. And after 1 year of discussion, we managed to have this signed agreement between 4 centers, which are Rome, Palermo, Padova, and Turin. But of course, this is a wide agreement for which basically all centers of INAF can participate. And so the point is to advance not only gamma ray burst field, but also other fields for which both INAF and NAOJ are expert. Now, there are also ongoing agreement, and I would like to tell you this because, of course, if in the audience there are people that would be interested in both the scientific topics run at NAOJ and they would like to make some proposal for agreement, I'm actually helping NAOJ in this direction. So we have Sokendai University of Salerno agreement, and the other way there is a Sokendai University of Turin agreement. As I said, we are open to other agreement to be held. So now, what are gamma ray bursts? Gamma ray bursts are high energy flashes in the sky. Their typical duration is few seconds. And actually, in the same amount that they release, the same amount of energy that they release in few seconds, our sun releases in its entire lifetime. So this is to give an example of how strong in terms of explosion these objects are. And not only we have the emission in gamma rays, but also they span over several wavelengths, gamma rays, optical and radio. And because they are among the most energetic phenomena in the universe. Actually, they can probes of the extreme physics and distance cosmology. We have already heard about the importance of the understanding of dark matter and dark energy. And actually, I also would like to connect my talk with the experiment of light bird for the signal of the primordial universe. So currently, we have this problem that we don't know what it is, the current Hubble constant tension. So gamma ray bursts, because they are middle way, and I will tell you in a moment, they can help actually to see whether there are, for example, some exotic equation of state for dark energy or dynamical dark energy. Now we see that this is the example of gamma ray bursts that they span over several order of magnitude, but the audience is pretty expert, so I don't go into detail of this. And again, they are so powerful, as I said, that they release in few seconds the same amount of energy that our sun makes in 10 billion years. But so why it is also not only important to understand the mechanism of gamma ray bursts, but also what it is the distance of gamma ray bursts from us. Because again, we can explore the fundamental particle physics at the very high energy. And then, sorry, I think so we can understand how the universe evolved over time and what were the properties of the universe. Again, we go from the Big Bang, because they are observed up to redshift 9.4. It means that we are at really close to the most distant galaxy. Although now with James W. Webb we have observation up to redshift 14. And how fast is the universe expanding, so we can also measure the acceleration of the universe, and how many types of gamma ray bursts are. And this is very important, because according to the type of gamma ray burst, then you can build standard candle, and this type, then they can highlight what are the parameters of the universe: dark matter, dark energy, and the acceleration. And then we can again explore fundamental particle physics at very high energy. Now, I already covered this, saying that the gamma ray bursts are very among the most explosive phenomena in the universe after the Big Bang. And actually, it is important to have also not only satellite mission, but also ground-based observatories, like, for example, the Subaru telescope that can observe at very high redshift, and all the other ground-based facilities in optical to obtain the afterglow of distance event. So because the afterglow has been one of the main, discussion, especially in the past 20 years. But now I would like to go a little bit with the history. So it's very intriguing, the fact that gamma ray bursts have been discovered by chance because of this nuclear treating banning the nuclear weapons. So those satellites were observing serendipitous observation of high energy gamma rays, which of course could not be due to nuclear weapons, but these were indeed gamma ray bursts. And for a few years, then people didn't bother about this, until then a few more observations arrived, and then the kind of understanding of gamma ray bursts, to try to understand the flavor of gamma ray bursts. So there are two types of gamma ray bursts. The long gamma ray bursts, typical duration is greater than 2 seconds in the main events, and they are coming from the collapse of massive stars greater than 30 solar masses. And the short gamma ray bursts, instead, they are coming most likely from the merger of two neutron star or neutron star black hole. And if we consider neutron star radio of 10 kilometers, these are extreme dense objects, and we have the observation of the gravitational wave event in combination with the GRB happened in 1708, so August 2017. And this has opened a new era, the multi-messenger era, for the observation of the GRB in combination with gravitational waves. Now, this it's a bit more technical, how to say, slide about the distinction between long and short gamma ray bursts. And again, I would like to insist on the fact that when you build relationship among variables on gamma ray bursts, you need to be sure which type you are using, because according to the type, you have different mechanisms behind it. And here there are several definitions by Batze and so on. But now, again, I already anticipated the importance of gamma ray bursts as cosmological tools, not only for the dark energy and dark matter contribution to the universe, but also they can be probe of the early evolution of the universe. Indeed, this few years we have seen the discovery of James W. Webb, that has seen that the number of galaxies actually has surprised us with a number that it was not expected. So we need to understand what it is, the formation of gamma ray bursts in terms also of the galaxies, and they are beyond the epoch of reionization. The epoch of reionization can be put at redshift, the end of the epoch of reionization at redshift 6, but this is a little bit blurry, and we can investigate population 3 stars, track the star formation. They are much more distant than supernova 1A, so we will have the advantage again to have exotic models, for example, for the evolving dark energy model. But their problem is that their prompt luminosity, that it is the main event in gamma rays, they span over 8 orders of magnitudes, and because of that, it is very challenging to build them as cosmological standard candle. But now I would like to go through a review of the satellites and missions that were helping to observe gamma ray burst. So here we have the Italian-Dutch mission, BeppoSAX, that in which basically we had the first X-ray mission capable of simultaneous observing targets over 3 orders of magnitude of energy. As I said, the gamma ray burst span over several orders, from 0.1 to 300 kV, with imaging capability and a spatial resolution that by that time was pretty good, 1 arcminute between 0.1 and 10 kV. And what was the discovery of this mission was that actually gamma ray bursts are, well, the afterglow of gamma ray bursts. So gamma ray bursts could be seen not only in gamma ray, but also in optical. And here it was the main flux versus time distribution. But this is actually an ancient one, because then the real behavior of gamma ray burst is not a simple power law, but it has many more flavors. And now, going to another important discovery, besides the optical counterpart, is basically the definition of the determination of the redshift, because at that time we were even not sure whether gamma ray bursts were galactic or extragalactic. So this opened up a new, incredible, amazing era. And then the takeaway of BeppoSAX is that we can definitely open a new era, understanding the GRB physics and possible application of GRBs as cosmological rulers, but we need to wait to Swift to see more detailed light curve and more possibilities for their emission mechanism. But the bandwidth of Swift is small, so does not allow us to identify the peak in the spectrum, and therefore we also need to wait for Fermi and Agile. And Fermi actually is a very good example of Italian, Japanese, and US collaboration, which is still ongoing. So the Swift mission was launched in the Swift mission was launched in 2005, November 2004, but actually the GRBs with the redshift came in 2005, and it has a very good localization. So we have and also quite good angular resolution for the UVOT position in terms of timing. So the data for Swift are publicly available, and because of that, many scientists from Japan and all over the world are using this, and also use this data in combination with other missions. So many efforts are also to trigger on SWIFT mission. That's why SWIFT remains one of the most relevant mission for gamma ray burst. Now, if we consider, I'm sorry. So as I said, I showed you before that was a simple power law, but actually the situation is much more complex than this. So you see a spike, then a decay, and then this flat part. And we have this golden sample that it is when you have GRBs with very flat plateau, you can use them then as cosmological standard candle. So this is what it is happening now with the SWIFT is quite worrisome, but also not so much, because we have the catalyst space technology that will rise the SWIFT orbit in summer 2026. So with that, we can go on with the SWIFT for a few more years. And as I said, a very good example of connection between Italy and Japan is with the Fermi-LAT telescope. So Fermi-LAT has observed more than 200 gamma ray bursts and around more than 40 with the redshift, and the GBM monitor has observed more than 4,000 GRB events. So these have been very prolific mission. And one important point is that thanks to the GBM and the integral localization, we could have had then the localization, the coincident observation of the gravitational waves with the short gamma ray burst. So this has again revolutionized our understanding of gamma ray burst. And here we can see also the many wavelengths in which this has been observed. So this again points out to the importance of the multi-messenger astronomy. And then we have the Agile, that it is a completely Italian mission, which also has one of the key highlights of Agile has been the detection of high energy, which shows to have tail that it is longer than what we expect. And this is also something that we observed then with the Fermi-LAT. Then the Calais mission, there is a next talk that will speak about this, but I would like just to say about that it is important also for gamma ray bursts, because it observed also almost 500 gamma ray bursts, basically around 42 gamma ray bursts per year, and it is still ongoing. And especially it is important for the soft X-ray. Then we have the Hitomi mission. Then that although it was not, it had a problem during the launch. It had many science cases that could be explored, like the large scale structure, evolution of the universe, distribution of dark matter within galaxy cluster, how the galaxy cluster evolve, and how matter behaves in strong gravitational fields. Also, it could have explored the physical condition in region where cosmic rays are accelerated, as well as observing supernovae. But luckily, data were retrieved, so that also observation of the Perseus galaxy cluster revealed insight into the motion of gas and behavior of matter around a supermassive black hole. And these are the specifics of the mission, but I think I don't have a lot of more time left. So I will just tell you a little bit about what are the future mission, the effort of the Japanese community in terms of gamma ray burst are with the IZ Gundam mission. And this is a fully Japanese mission, but there are a lot of collaboration between this Japanese mission and the Italian mission, Italian, UK, French. It's more European collaboration. But also there is a lot of discussion between Theseus and IZ Gundam. IZ Gundam will be launched before Theseus, but this is a smaller size mission than Theseus. But this will be, once the launch will be contemporaneous, will be also complementary. And there are also CubeSat mission for this regard. So now, why I would like to end with a more technical slide, because why this mission is so important in high energy, because basically one of the current issue here is that you can see that the star formation of gamma ray burst, the star formation that it is pinpointed by the galaxies, that it is these many lines, solid lines, actually do not agree with the density rate evolution of gamma ray bursts at low redshift and the high redshift. So we need to understand what this situation is. So we had this paper. These are two pictures taken from DAINOTTI et al. 2024, published in a PJ letter, in which we show this, and also we gave in additional papers explanation that possibly low redshift gamma ray bursts come from the mergers and are different from the long gamma ray bursts. But other interpretation is that these are low luminosity gamma ray bursts, and also there is more production of gamma ray bursts that you see at high redshift respect to what you expect. And this is also important for the shape of the luminosity function. And now I would like to conclude because I think my time is up. So if I have another minute. Yes, so then I would like to also mention that it is very important to distinguish two distribution, the red points and the orange point and this purple point, because those are with and without the selection biases. So if we do not consider selection biases in your sample, then you can have a mismatch. And so this is important to do. So then the concluding part is that we really need gamma ray mission to reveal extreme phenomena and processes. And so space missions are essential, but also ground-based observation, again, like the Subaru telescope and many others, are relevant for the GRB science and for the multi-messenger astronomy. And Italy and Japan has driven this collaboration, even with many scientists, because of the time zone, making lots of effort in meeting in different time, like Fermi-LAT collaboration. In Japan, we meet at 1 a.m. in the night, and 7 a.m. in US, California time, and 5 p.m. in Italy. So all this effort from this community is really something that drives the science. And then we will help with the gamma ray bursts to explore the early universe. So the public data also is a key point. All these missions that I mentioned have this public data. And so the suggestion is that if we are still waiting for the big mission to go, I think we can start the discussion about joint CubeSat mission. Thank you so much.